Hello and welcome to my talk. I'm Thomas Kesselheim from University of Bonn, and I'm excited to present joint work with Paul Dutting, Ezra, and Michal Feldman on combinatorial contracts. I'm not sure how much you've heard of contract theory, although it is actually a central topic in microeconomic theory and has been since the 1970s. But as it turns out, people have started asking computational questions, like how to compute optimal contracts, only very, very recently. The central question in contract theory is how we can incentivize people to work. What's that supposed to mean? Maybe let me give you an idea of what a very simple example might look like. Suppose you own a website and you want to attract more visitors to that website. To this end, you can hire a marketing expert, and that marketing expert can make posts on social media, pay influencers, spread the word, whatever. You actually do not observe what that marketing expert is doing, you only see the effects of this, namely more visitors to your website. And now what you want to do is you want to set up a contract with this marketing expert so that they are actually incentivized to take the best actions to attract more visitors. How could one model such a problem mathematically? We have a principal and an agent. The principal in our example would be the website owner, the agent would be the marketing expert. This principal is pursuing a certain project which they hope will succeed. This is just a binary outcome that we're modeling here. This project will succeed with a certain probability, and in this case the principal gets a reward of 1. How will that happen? Well, the agent has the choice between multiple actions. They can choose one or multiple actions, and based on that the project succeeds with a certain probability. So if the agent chooses actions S, then the success probability will be f of S. But choosing actions comes at a cost for the agent. They incur cost C of S depending on which actions they choose. So far the agent isn't incentivized to do anything because, well, everything just comes at a cost. This is why the principal now defines a contract. And a contract in this case is nothing but a real number between 0 and 1, which we call alpha. Based on whether this project is now successful or not, the agent will get a compensation in the case of success. So they will just get alpha if the project is successful and 0 otherwise. What would now be the principal and agent's expected utilities? Well, as I was saying, the principal gets a reward of 1 with probability f of s if the project is successful, but out of this 1 reward, they will have to pay alpha to the agent, which means that the remaining expected utility is 1 minus alpha times f of s. And what about the agent? Well, the agent will get in expectation a compensation of alpha times f of s, but they will incur a cost of C of S, so the expected utility will be alpha times f of s minus C of s. Our optimization problem is now to maximize the principal's expected utility. So 1 minus alpha times f of s. But S is chosen by the agent who maximizes their utility. So this S is chosen so as to maximize alpha times f of s minus C of s. Let me make a few more comments on what is known and what is not known. Actually, almost everything is known. We assume to know which actions the agent can choose. We assume to know which success probabilities these will yield. We assume to know which costs they will yield. But there is one thing that is not known, and this is kind of implicit in this formulation. This compensation may not depend on the actions chosen by the agent. It may only depend on whether or not the project was successful. So our goal will be to compute an optimal contract a best alpha from the principal's perspective. And we want to do this in time polynomial in the number of actions. That's quite easy and doable if the agent takes only one action, because then for each action you can figure out, is there a way to incentivize the agent to take it? What's the cheapest way to do so? But our question is now, what if the agent takes multiple actions? Then this naive approach will not give you a polynomial time algorithm, just because the agent now has exponentially many choices in the number of actions. In our paper, we show that sometimes it is still possible to compute an optimal contract in time polynomial in the number of actions, but sometimes it is not. Let's now first introduce the optimization problem a little more in detail. So we have these n actions, 1 through n, and each action has a cost for the agent, C of A, it's just a non-negative real number, and the cost for the agent to take a set of actions is nothing but the sum of the costs of the individual actions. So the costs are simply additive. This is different for the success probabilities. F of S, this will be the probability of success of our project when the agent chooses set of actions S, just any subset of the actions A. And this success probability function F maps from the power set of the actions to reals between 0 and 1, but this is not necessarily additive. In fact, what we'll assume instead is that it has diminishing returns, meaning it is a submodular function or a special case of a submodular function. Fortunately enough, there is a well-established hierarchy of classes of such functions which actually have their origins in combinatorial auctions, but which we can also apply here. Namely, this can be a submodular function, or as a special case, it can be a gross substitutes function, which would still be a generalization of unit demand and additive functions. So this is the input to our problem, these costs and the function f, the probability success function. And now the optimization problem is as simple as follows. We want to find an alpha that maximizes the principal's utility, 1 minus alpha times f of s, where the set S is exactly the one that maximizes the agent's utility, which was alpha times f of s minus c of s. And because this maximizer of the agent's utility might not be unique, we have an additional assumption, namely that the agent will break ties in favor of the principal. So what are our main results? Our first main result is that if the success probability function f is gross substitutes, then the optimal contract can be computed in time polynomial in the number of actions given access to a value oracle. This class of gross substitutes function, that's actually well established in combinatorial auctions. It is defined by how an agent would react to changing prices. And I think it's interesting to see that this class of functions also admits polynomial time algorithms in this combinatorial contract setting. What if we go beyond gross substitutes? Well, what we show is that if these functions are budget additive, which is another subclass of submodular functions, then computing the optimal contract is NP hard, which means that for general submodular functions, such a result like our first main result will not be true unless P is equal to NP. And we have further results, namely for any kind of success probability function, not even submodular ones, arbitrary success probability functions. There is an FPTIS to compute an optimal contract, but that assumes that we have access to a demand oracle. And furthermore, we extend our results beyond binary outcomes, but unfortunately I don't have enough time in this talk to go into details about that. Instead, I want to focus on this first main result, namely how can we compute an optimal contract in polynomial time given access to a value oracle if the success probability function is gross substitutes. And to understand that, let's have a closer look at a particular example of just actually an additive success probability function. So that's actually a special case of a gross substitutes function would be just an additive function. So as I was saying, the costs, they are always additive. So CFS is always the sum of the CFA. But now we'll also have an example where f of s is the sum of the f of a. So what's the agent's utility? This depends, of course, on the set of actions that the agent chooses, but also on the contract. If the contract is 0, alpha is 0, this means that the agent is not getting any compensation. The utility will be negative, it will be just minus CFS. If the contract alpha is equal to 1, then the utility will be f of s minus CFS, which in this case is positive. But the agent could, instead of choosing actions 1 and 2, might also, for example, not choose any action. This will always give them 0 utility because it makes 0 success probability, but also 0 cost. And you see, sometimes it's better, sometimes it's worse than taking actions 1 and 2, but sometimes it's even better to only take action 1. And then, sometimes it's even better to take all 3 actions, 1, 2, and 3, if the compensation is pretty high. But now the crucial property is that it is actually never optimal for the agent to take, for example, only action 2 or actions 2 and 3. Because if we look at this picture from left to right, we see, okay, the sets that maximize the agent's utility are the empty set, the set containing only 1, the set containing 1 and 2, and the set containing 1, 2, and 3. And this is now what it looks like when the agent chooses the respective set so as to maximize their utility. It is just the upper envelope of all these lines. And you see one important property, namely if you look at this from left to right, you see that always one further action is being added to the set. And this is no coincidence here, because the function is additive. So action by action, the agent will decide, is it now a good idea for me to take this action? Is the expected compensation high enough to cover my cost or not? Okay, now let's switch to the principal's perspective. We know that so far in this interval the agent takes the empty set, here they take the set that contains only 1, and so on. Now what does the principal's utility look like? This, as we know, depends on what the agent chooses, so we'll get a different function in each of these intervals. But now, of course, each part is decreasing in alpha. And so what we see here is that there are actually only a few interesting points for our contract alpha. Namely, it is, looking at this from left to right, these points where the agent changes their choice of the actions. And these points we call critical points. And they play a crucial part in our way of computing the optimal contract. Namely, what we show is that if f is gross substitutes, then the optimal contract can be computed in time polynomial in the number of critical points and the number of actions. And also that if f is gross substitutes, then the number of critical points is bounded quadratically in the number of actions. So if you combine these two results, then you have immediately your polynomial time algorithm for gross substitutes functions. This first part isn't trivial, but it's not super complicated. It is actually just doing exactly what you would expect, namely, in this diagram that I was showing on the previous slide, just go from left to right and keep increasing your alpha, and this way you can iterate over all possible critical points. The second part that is more difficult to show, and I'll give you some more ideas on how we show that in the remainder of this talk. Before going there, let me make two more remarks. How important is it that f is gross substitutes? Well, for this first result, it is important but not crucial, because we also have a weaker result for general functions. Weaker in the sense that the running time will be worse and the assumptions are stronger, but generally you can still do similar things. But the second result, for this, it is crucial that f is gross substitutes. This does not hold for general functions. It doesn't even hold for coverage functions, which are another subclass of submodular functions. So here we crucially use this gross substitutes property. So let's have a look at how we prove this second lemma. If f is gross substitutes, there are only quadratically many critical points. I hope you recall that these critical points were always these left endpoints of the intervals where the agent changes their strategy. But before, in the example of an additive function, this was always just adding one further action. Now, if you have a gross substitutes function, this is not necessarily true. What might happen is that sometimes you also remove an action from the set, or the agent will do that as a best response on that particular contract. But there is still a certain structure to this. Namely, what we show is that at each critical point, looking at this picture from left to right, either an action is added to S or an action from S is being replaced by one with higher cost. We show this property via a more careful analysis of what the agent actually maximizes. Recall that the agent is maximizing their utility, so this will be alpha times f of s minus c of s. But this is actually equivalent to maximizing f of s minus 1 over alpha times c of s just by dividing this term here by alpha. And what you now can see is that this is actually something that looks very familiar to us. Because these costs were additive, maximizing this quantity is exactly what you would do if you were a buyer who has the choice between multiple items. Each action corresponds to an item, and your value for the items is defined by f, and you'll have prices for the items defined by 1 over alpha times c of a. And so these sets S that maximize this, these are exactly the ones that are demand sets of this particular buyer. And this demand relation and how it changes when you change item price, in the case of gross substitutes functions, that is actually well understood, but it's only well understood if you change item prices one by one. This is now not what we're doing here. The item prices are now just changing all simultaneously because we are now interested in how the demand changes as you increase alpha, so all these item prices decrease simultaneously. But as we show in our paper, also this structured property follows from the gross substitutes property. Having shown it, because we still want to upper bound the number of critical points, we have to upper bound the number of such transitions. And we do so by using a suitably defined potential function, which then gives us an upper bound which is quadratic in the number of actions. So let me wrap up here. What we see is that depending on our assumptions, we can compute the optimal contracts in polynomial time, or sometimes it's also hard. And what I find interesting is that we have intriguing similarities but also differences to combinatorial auctions compared to this combinatorial contract setting. What are open problems? Well, we might, for example, want to better understand other class of functions, other subclasses of submodular functions, or maybe also functions which are not submodular at all. And another question would be, what could we do if there are multiple principals and or multiple agents? Although I should add that first you would then have to define a new model for that setting. So thank you very much for watching my talk video. Please reach out to us if you have any questions, and of course, stay safe. Bye.